Good evening. My name is Claire, and we are working on the multi sparse learning for voice pathology diagnosis with weekly self-supervised knowledge distillation and the contents of the presentation. Then here we have the background and we have the mouse strategy, and it's all about combining multiple techniques. It's all about combining multiple techniques used to train a model in order to improve the model's robustness and performance across different voice conditions in the data set used. Like some of the techniques, we have the sparse learning that is all about extracting the relevant features like the abnormal jitter, while ignoring the irrelevant variations like the background noise, reducing the computation costs, and it enhances the model interpretability for the clinicians, and the signal processing that involves cleaning and preparing the audio data. Here, the signal processing is the backbone for the voice pathology analysis, and it involves transforming the raw, the noise audio into clinically meaningful features that machine learning models use to diagnose disorders. And also another part, we have the sparse learning that focuses on identifying the most relevant features in the data set. And this reduces the redundancy. And continuation, here we have the weekly self-supervised learning, and it trains accurate models on limited label data. In the medical datasets, often lack the annotations due to the privacy, and weak supervision bridges this gap, enabling the models to generalize even with the sparse expert label data. And for the knowledge distillation, it deploys efficient model for the real world, and it's all about the deploying the lightweight models on edge devices like smartphones enables real-time voice analysis in clinics. Like distilled model could screen for pathologies during the remote patient consultation, and the pathology diagnosis, it enables to know the root cause of the voice disorder. And here we have the literature review. We're starting with a voice pathology detection system using deep learning on the mobile healthcare framework. And this one, the voices are captured using the smart mobile devices, and voice signals are processed before being fed to the convolutional neural network. And the hierarchical classifier that aims in automatic classification of voice disorders while using approaches that reduce data redundancy, since the available data for training model are scarce. And another, we have the speech emotion recognition using the sparse learning. And here it's mainly to ensure emotions in the speech are recognized when people and computers talk to each other. And we have the weekly supervised learning framework for detecting the social anxiety and depression from the long audio clips. And this one detects the individuals high in the symptoms of the two mental disorders, the social anxiety and the depression, from the weekly labeled audio data. And another one, you have the compact and domain robust voice disorder classification system, identifying the arteries of health, neoplasm, and benign structural diseases. And this one is all about, it creates a small and a strong system that can listen to someone's voice and figure out if the voice is healthy or has a tumor or has a non-cancerous problem. And another one, a survey on the signal processing. This one it involves using non-invasive signal processing technique to detect the voice disability in general population. And problem statement, we have the domain application problem, and people worldwide with voice disorders face communication difficulties in everyday life, and the current voice pathology diagnosis methods are based on the subjective perceptual assessments, speech language pathologists, and other specialists. Yet this can lead to the misdiagnosis and delayed diagnosis, hence worsening the condition. And for the computation problem, we have the existing models are invasive, like many current diagnostic models for voice pathologies require invasive procedures such as inserting cameras and sensors into the patient's throat to observe the vocal fold behavior. And these methods are uncomfortable, they are expensive, and they need the skilled medical personnel. And the research questions and the objectives have to enhance communication for individuals suffering with voice disorders and to implement an accurate and efficient voice pathology diagnosing model to ensure real-time processing and accessibility, and to deploy the model on a user-friendly platform. And the research questions we have: which acoustic features are most effective for distinguishing between the healthy and pathological voices? And what are the most, and the second question is, what are the most effective feature extraction methods for identifying relevant patterns in the audio signals for voice pathology diagnosis? And the research contributions and output: we developed an efficient voice pathology diagnosing model. We built the first advanced assistive communication technology, and we developed a speech impairment model, and we developed an enhanced real-time processing for practical use. And here the flow diagram for the methodology flow diagram. We started with the data collection and pre-processing. Then we did feature extraction using the sparse learning, then model training and knowledge distillation. The model that we deployed, we used, it was implemented with knowledge distillation, then model prompting, since it outputs diagnosing results in text form, and the output generation. Then after, it outputs the diagnosing results. Let me invite my colleague Emma.
Good evening, everyone. This is Emmanuel Asimu, and I'll be taking you through the dataset description and exploratory data analytics. So the dataset we had consisted of voices of sick patients and healthy patients. So these were voice clips of children who had speech, who were sick. Like some were sick, some were healthy. So it was collected from, we got a link called Lindat. So we got that that was where that's where we got our data set from. But in the data set, we had very clear voices and unclear voices. So these are the voices we extracted out and used in developing this model. So the output results, among our output results, we had this graph, for example. So you realize that there was a data imbalance between healthy and sick patients. So you realize that these are the samples of healthy children are 1,000, while those of the sick patients were 2,000. So this created a data imbalance among the healthy patients and the sick children. So we had to balance the data to reduce this imbalance so that we have almost the same samples to carry out the model development. So you realize that even in the spectrograms and other analytics, you realize there was a concentration of the voices for healthy patients in some point, and then there was a very high concentration for the sick patients at some point. So here it was a bit uniformly distributed as compared to the one for the sick patients. So we looked at the output results. They gave us a picture of how our data looks like and where we should tackle and the techniques to employ to handle these inefficiencies in the data set. So these were the EDA results we first got. And these, so we had to rate the precision and the recall values. So we rated them So class 0 was for the sick patients, like sick children, and class 1 was for the healthy children. So these are the models we developed. So this was a linear regression. This was a SVM model, KNN model, and the random forest. So we developed these multiple models to help us understand their accuracy and precision. So then we also had the correlation matrices and the spectrocentric. So we also developed these graphs initially to really understand what's in the data before we employed the other techniques such as sparse learning, weakly self-supervised learning, and also the explainable AI techniques. So the explainable AI techniques, we used layer relevance propagation. We also used SHARP to develop this graph. So at first, when we deployed the sparse learning, we were able to sort the data into the data sets that were relevant. We picked out the relevant data and used them. Then we used weakly self-supervised learning to get the data that had the data that had labels. Remember, this data had labels, but we had to select the data. We had to select the data with the labels, the unlabeled data among that data so that we could be able to develop our model. So we employed multiple techniques, including the explainable AI techniques. At first, we had a problem with the explainable AI, employing the explainable AI techniques because of overfitting, since the data had issues. So when we employed these techniques such as feature extraction, we left out some, got what we want to use. So we are able to obtain this data set and we're able to employ layer-wise propagation. So these are the graphs for the explainable AI. So among these models, we're able to select the best models, the worst models. So we selected some of the good models that we expected to get. And after getting those good models, we managed to do model fusion. So we did model fusion. After doing model fusions, we developed a fused model. So this model was combining all the techniques and all the other models, the strength of other models. So this model was developed and it was able to, it was the model we deployed. So we selected that model that we had, after selecting the various models, so we developed that model that was very good for us and we were able to deploy it. After deploying this model, so this is how it works. So this model is able to predict and diagnose for an illness. So the client is supposedly supposed to maybe record their voice or maybe submit an audio clip. So when they submit the audio clip, we get a diagnosis. We get a text, maybe the voice is clear, maybe the voice is for a sick person, the voice is cancerous, the voice has issues, or maybe the voice is healthy. So this model was able to predict and diagnose this patient. So this is the speech impairment model. So we actually had problems with deploying it on Crane Cloud. So on Crane Cloud, we were using the zero crossing rate to actually put the values. So you get a zero crossing rate and then it gives you an output. So on the Hugging Face, we deployed this model and it was deployed successfully. So the next steps, we're going to upload audio files directly instead of first extracting the zero crossing rate. As I explained to you, we had issues with the Crane Cloud, but we were able to deploy the model whereby you apply a zero crossing rate, a certain value of the zero crossing rate, and then you get a value. But then remember, there is an accuracy problem because our model had 80% accuracy, which is not very good as related to other models, which could, especially for this field, which is diagnosing a person. So the accuracy of 80% is really low because even 98% is not the best. So we want to improve our accuracy, and then we also hope to be able to upload audio files directly on the Crane Cloud. Then we also hope to diagnose as many health conditions as possible. So in the process of diagnosing many health conditions, we'll be able to get the audio clips and retrain the data set so that we can have very, very accurate diagnosis. So I acknowledge our lecturers for being with us. We also acknowledge Unipod that supported us, the invisible forces and the visible forces that put in their efforts to make sure that we've been able to present and develop our machine learning model. your efforts will not be taken for granted. Thank you very much.